Welcome to True Projects. In this video, we are going to explain about the project that is Transformative Transfer Learning for MRI Brain Tumor Precision Innovative Insights. So before getting into the execution, first let us understand what is the project about. Human brain. Human brain, it controls everything from how we think and feel to how we move and react. Because it is so important and complex and it is also very vulnerable to serious problems, one of which is brain tumors. So these brain tumors, they happen when cells in the brain or spinal vessels, they start growing abnormally. Some tumors are benign, meaning they aren't cancerous and they grow slowly, while the others are malignant, which are cancerous and more aggressive. So doctors, they often classify them using the WHO, that is World Health Organization system, which grades tumors from grade 1 to grade 4. Grade 1 is least dangerous and grade 4 is most aggressive. So to detect these tumors, doctors they mainly use magnetic resonance images, that is MRI. MRI scans give very clear, detailed images of the brain showing the size, shape, and location of tumors and help to distinguish normal tissue from abnormal growths. So, however, reading MRI scans isn't always easy. Patients have to stay very still during the scans, which can be difficult, and certain people can't get MRIs at all because of implants or other medical reasons. Also, brain tumors can look very difficult, that is, very different from one patient to another, which makes interpreting the images more challenging. And here, the traditional methods for this MRI based detection, that is, MRI based classification, have the issues like thresholding, valve based SVM, or texture analysis. So, these are the traditional methods, often struggle because brain tumors can look very different from patient to another. These methods aren't always able to capture all the variations in the shape, size, and texture of tumors, which can lead to mistakes or less accurate diagnosis. And moreover, the challenge is that high quality labeled MRI dataset is hard to come by and expensive to create. Without enough data, it is difficult to train new models from scratch that can reliably detect tumors. Because of these limitations, it is hard to deploy these methods effectively in real hospitals, where doctors need tools that are accurate, fast, and consistent. In short, the problem is figuring out how to handle the variety in tumor appearances and limited data so that we can create models that reliably identify brain tumors and help. So here to overcome from all such issues, the system it uses something called transformative learning, that is TTL, to detect brain tumors from MRI scans more accurately. Instead of training a neural network completely from scratch, it takes advantage of pre-trained deep learning models like VGG16, ResNet 50, Inception V3, and DenseNet 121. These models have already learned recognizing patterns from very large image data sets like ImageNet. So by fine-tuning these models on MRI images, the system can apply what the models already know to the specific task of identifying brain tumors. This approach has two big advantages. That is, it requires less medical data than the training a new model from scratch, and it improves the accuracy and also performance of tumor detection, making it more reliable for clinical use. And here, before Before feeding MRI images into the model, the system applies a structured pre-processing pipeline. This includes resizing images to the required dimensions, normalizing pixel values, reducing noise, and also performing data augmentation like rotation or flips. So here we will be doing data augmentation as well. And here, after that, once the pre-processed, the TTL model extracts the important features from the MRI scans, using them to classify tumors. Compared to traditional methods, this approach is more effective. And here, the system performance is measured using metrics such as accuracy, sensitivity, specificity, precision, recall, and FN score, showing that it can reliably detect brain tumors. Overall, this makes the system more robust and efficient tool that can assist doctors in making better clinical decisions. And moving on to the improvisation of the project, to further improve the performance of this project, additional models and features were added as an extension. So the first thing is adding exception model and the ensemble model, combination of exception and DenseNet. So these are used on MRI dataset, which helps to improve the accuracy of tumor detection. And also, beyond the classification, here we have also added detection module. So the system doesn't just classify tumors, it can also detect and locate them within the MRI image. This is done using models from the YOLO family, which are designed to draw bounding boxes around abnormal areas, showing exactly where the tumor is in the scan. This makes the system more comprehensive and it can both identify the type of tumor and also highlight its location in the image. Also, we have added GradCam, so which is part of explainable AI technique. So this helps understand why the model makes certain predictions. So the system uses explainable AI technique, specifically GradCam. So GradCam, it generates heat maps on the MRI images, highlighting the regions that most influence the model's decision. This makes it easier for the doctors to see which part of the brain the model considered important for its prediction. And also we have added front end using Flask framework. So a user-friendly interface is created using Flask, allowing users to upload MRI scans and get the predictions from the trained models. This makes the system much more practical for the real-world use, as doctors or medical staff can quickly analyze images and see both the predicted tumor type and also areas of interest highlighting the scan. Moving on to the implementation. To implement this project, we have followed the steps which are mentioned in the flow of work. So these are the steps which are followed. Let's understand each of them. So first we have done classification. In classification, first we have collected the MRI images, each labeled with the type of tumor it contains. Then we divided the data into three sets, that is training, validation and testing, to ensure model can learn effectively and be evaluated properly. Then comes visualization. So the distribution of tumor classes is shown using a bar chart, helping to identify of any class imbalances. And also sample images from the dataset are displayed with their labels to verify that the data is correct and usable. And coming to pre-processing, so here images are resized to a uniform size and pixel values are normalized for consistency. And also data augmentation has been applied, like rotating the images, flipping brightness changes to make the model more robust. And data holders, that is data loaders, are prepared for training, validation and test sets to efficiently feed the data into the models. Then comes model training. So here transfer learning models and extension model have been used for training to improve the classification performance. So the models are trained in this stage. And that trained models are evaluated by using accuracy, precision, recall, FN score, confusion matrix, ROC, AUC. And the inference pipeline is when a new MRI image is given as input, the trained model predicts the tumor type along with a confidence code, providing a clear diagnosis. So this is how we have done classification. Now moving on to the detection. Here, first, MRI images are collected and they annotated with bounding boxes or YOLO format. So first, MRI images are collected and then annotated with the bounding boxes in YOLO format, that is .txt files, to indicate tumor locations. And the data is split into all the three folders, that is all the three sets. And coming to the part of visualization, sample images are displayed with the bounding boxes to ensure that the annotations are correct and precise. Then coming to pre-processing. So here, images are resized, normalized with the data augmentation applied to improve the model robustness, and a data.yml file is created which creates the path to the images and the class names, preparing the dataset for YOLO training. Then comes model training. So here, YOLO models, all the different versions of the YOLO have been trained to detect tumors, and each model learns both the location of the tumor, that is bounding boxes, and also the tumor types. And we will be evaluating all the versions of YOLO using mean average precision, that is MAP, precision and recall. Coming to the inference pipeline. So when a new MRI image is provided, the model outputs an annotated image with the bounding boxes and also confidence scores for each detected tumor. And coming to the part of front end. In front end, we will be uploading images. So this front end is developed using Flask web application. And here the classification, that is, if we have given images for the classification purpose, it will be classifying which type of tumor it is. And then coming to the YOLO, it will be localizing where the tumor is. And it will be displayed through the front end of the application. And moving on to the algorithms used. So these are the algorithms used for classification. So for classification, we have used VGG16, ResNet 50, Inception V3, DenseNet 121, exception, and the extension ensemble of exception with DenseNet model. And for detection, these are the different versions of YOLO that we have used in this project. To implement this project, we need two kinds of requirements, which are hardware and software. In hardware, we need operating system of Windows, processor of 5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. Software are application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, and front-end technologies are HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let's execute it. To execute, let's open the code folder of the project. So these are the source code files. Let us understand each of them. In this folder, we have the dataset. Let's open it. Here we have dataset in 4 different folders of 4 different stages. So here we have images of the brain where there is glioma tumor. And in this folder, we have MRI scans of meningioma tumor. Get back. In this, we have no tumor. So here we have no tumor. And here we have pituitary tumor. Get back. All these images, they are split it into train and validation. So images which are in train will be used for training and validation are used for evaluation. Get back. And this is a static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap, which are important for visual appeal. And here we have templates folder. This folder consists of files related to HTML pages that are used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And in this, we have test cases for both the classification and also detection that we will be using in the front end. And in this folder, we have the dataset that we have used for detection. So images which are in this folder are used for classification and images which are in this are used for detection. Let's open it. Here we have images in train as well as valid. So let's open train folder. Here we have images in the image folder and the bounding box coordinates in the label folder. Let's open images folder first. So these are the combination of glioma, meningioma, pituitary, and no tumor images. So we will be training YOLO models on these images. And annotation files that are the locations of that tumor in this labels file. Let's open. So here in this label folder, we have files containing annotations or labels for the objects in the corresponding images. So here, each label file, it corresponds to an image file in the image folder. For example, the first txt file, that is the first label file, it corresponds to this image, which provides the object locations. That is, it provides the locations of the tumor. Accordingly, for the second image, we have second label file. So for all the images, we have all the annotation files. And these files will be in the YOLO format. So let's open one file. Here, each line represents a detected object. Close it. Get back. So we have images in the validation also, but these images are used for evaluating the YOLO models. Get back. And this is the app.py file. So this .py file contains information related to front-end logic, and it includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And this is the model file which contain algorithm information. And these two are the Jupyter Notebook files, which contain a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells. So here in this Jupyter Notebook file, we will be loading this data set for classification and train the models. Accordingly, for detection, we will be loading images which are in this folder and train the models for detection. This is the signup.db file. This file is a database file which is used to store the user information. So this is all about the code folder. Now let's execute. Copy the path of the code folder from the address bar of the file explorer. I've copied it. Now open Anaconda prompt. It is opened. Give the command cd, give the space, paste the copied path, click on enter. We have not copied the path completely, so let's copy it again. Get back, give the command cd, paste the copied path, and now click on enter. So here if you observe, current directory is changed to the code folders path. Now compile app.py file. So give the command python space app.py and click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application locally at the default address, which is the local host and the port, unless configured differently. So just wait for a while. File is being compiled. So here is the link that is generated for application. So this is the local host and this is the port. Copy this local link provided by the Flask framework and paste it into any web browser. I have copied it. I prefer Google Chrome, so I will paste it in that. Paste the link here, click on enter. So this is the web page of the project, which is displayed in the browser. And this is developed using Flask framework. So this is the web page of the project. And here you can change the themes to light, dark, and auto. So here we have dark theme. And we also have the auto theme also. So this is the auto theme. So let's get registered first. Click on register and enter all the sign up details if you have not signed up. I have already signed up, so I'll directly sign in. Click on sign in. So give your username and the password. Now click on sign in. So we are signed in successfully and redirected to prediction page of the project. So here we will be doing prediction for both the classification and also detection. So first let's do classification. Click on classification. And here you can see choose file button, right? We're supposed to click on that for uploading the images. So click on choose file. Let's open test cases. As we're doing classification, let's open it. And we can upload any images from these folders. So let's try opening this one and select this image. Click on open and now upload it. Given image, it will be pre-processed at the backend. It will be fed to the trained model and then trained model will be giving us the classification result. So here we got the prediction that it is glioma tumor. And these are the recommendations for that. And this is the confidence score, which is 100%, that it is 100% accurate. And this is the uploaded image. And here we have the GradCam image. So this GradCam image, it highlights the region of MRI that the model considers most important for its predictions. So this red and yellow areas show high influence, indicating where the model focused to classify the tumor. It helps validate the model and support medical interpretation. So let's try uploading some more. Click on choose file. Let's upload image from the other folder. So let's try with this one. Click on upload. And here we got the prediction that it is predicting as meningioma. And these are the recommendations for that. And here also we have 100% confidence code. This is the uploaded image. And here we have GradCam image, which shows the areas where region of interest is giving the prediction. Let's try again. Click on it. Click on choose file. Get back. Open the no tumor folder. So let's try with this one. Upload it. Here we got the prediction that it is no tumor detected. And this is the no tumor detected. And this is the GradCam image. Let's try with the other image. Get back. Open this folder. Let's try with this one. So here we got the prediction that it is pituitary tumor. So this is the pituitary tumor and here are the recommendations for that. This is the uploaded image and this is the GradCam image. So now we're done with the classification. Let's do detection. Click on detection. Click on choose file. Get back. Open detection folder. So here we can upload any image of our choice. Let's try with this one. Click on upload and see what will be detected. So here we have uploaded MRI image. Here is the area where glioma tumor is present. It is drawing a bounding box around it and giving us the confidence score, that is how accurate the detection is in detecting this particular class. Let's try with some more. Click on choose file. Let's try with this image and click on upload. And here we got the detection. So this is the area where glioma tumor is present. Let's try with some more. Click on choose file. So let's upload this one. Here we got the prediction. So this is the area where meningioma is present. And you can see a bounding box is drawn around it. Now let's try doing prediction with other image. Click on choose file. Now let us upload this image. So here also you can observe meningioma has been detected. Now we'll try with some more. Click on choose file. Now let us upload this one. So here you can observe there is no tumor which is drawn in white color bounding box. Let's try with the last image. Click on choose file. Drag down. Let's try with this one. And here you can observe there is pituitary tumor which is drawn in the sea green color bounding box. So in this way, you can try doing detection. So coming to classification, when we have uploaded the image and given to the application, it was only just telling which type of tumor it is. Coming to this detection, it is highlighting the area. It is drawing the, that is, it is localizing the area where that tumor is present. So this is the difference between detection and classification. So that is why we had added this detection part as an extension. Now let's check with the graphs. Click on classification. So let's check graphs of classification. And here the first graph we have is the number of images per class. So here on x-axis we have classes that we are predicting, and on y-axis we have number of images of each class. Get back. And here we have number of images after splitting. So these are used for training and these number of images for validation. And this is ROC AUC. Get back. This is the confusion matrix of the extension model. And here we have accuracy comparison graph. Here on x-axis, we have all the models that we have trained, and on y-axis, we have accuracy. Here, if you observe, ensemble model has the highest accuracy. Accordingly, we have for precision, recall, and FN score. And this is line and stacked bar graphs. So here on x-axis, we have models, and on y-axis, we have scores. And red color represents precision, green represents recall, orange F score, and blue is the accuracy. This is line plot of the matrix by all the models. And this is the stacked bar graph. So this is the stacked bar graph. And here we have stacked precision with recall. Get back. We are done with the classification graphs. Now click on detection. So here we have graphs of detection. So this is the YOLO model. Here on x-axis we have all the algorithms that we have trained, and on y-axis we have precision score. Accordingly, we have for recall and also mean average precision. So we are done with the graphs. Now click on log out. In this way, just by giving images to the application, we will be getting the detection. If you want classification, it will just tell you which type of tumor you have. If you want detection, it will localize the area where tumor is present. So in this way, we can automatically detect the brain tumor from the MRI scans by using the transfer learning models. This is all about the project.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.